Hello, and thank you all for joining us today. We are very pleased to have F J Duarte with us for this webinar, as he introduces us and his book and the research surrounding one of the most mysterious and promising subjects in physics, the fundamentals of quantum entanglement. Dr. Duarte is an award-winning laser physicist who is a fellow of the Australian Institute of Physics and the Optical Society. As an expert in the field of narrow line width tunable lasers and their applications, Dr. Duarte has a vast knowledge and research experience in coherent imaging, high-power tunable lasers, interferometric microscopy, laser metrology, laser oscillator physics, quantum interference, and numerous other related fields. He is currently exploring the physics of organic semiconductor coherent sources and quantum space-to-space communities, which are rapidly developing fields with exciting horizons. During the webinar, we welcome your questions, so please use the Q&A facility to send them in at any time during the talk, and we will try and answer as many as we can at the end of the presentation and respond to any unanswered questions once the webinar is over. So on that note, I shall hand you over to Dr. Duarte.
Oh, thank you very much, Evie, for that nice introduction. We are going to describe the best we can the recently published book, Fundamentals of Quantum Entanglement. Oops, I can't. Oh yeah, there we are. And that's the cover of the book. Now, this book has about 240 pages, 29 chapters, 10 appendices, about 70 figures, some 700 equations. The book is almost entirely self-contained. That is, you do not need to run to the library to get additional information. And it was written specifically to cater the knowledge bases of people with a background in first-year algebra and first-year calculus. Some of the ideas on quantum interpretation are an extension of what was already published in Quantum Optics for Engineers in 2014. The objectives of this presentation are to provide an overview of the physics included in Fundamental of Quantum Entanglement, outline the two paths to quantum entanglement, that is the philosophical path and the physics path, describe the interferometric origin of the probability amplitude of quantum entanglement, outline the generalized equations for quantum entanglement, provide an introduction to matrix notation in quantum entanglement, briefly outline some applications, and discuss some of the issues in quantum interpretations. Nothing describes better this book than a statement written by John Clyde Ward in the year 2000. That statement says, xy minus yx in Dirac's ket notation was my first lesson in quantum mechanics, and in a very real sense my last, since all the rest is mere technique which can be learned from books. You will recognize that xy minus yx in ket notation is the probability amplitude for quantum entanglement. Now, there are two ways to approach quantum entanglement. The philosophical path, which most of you are familiar with, that was the path created by Einstein, Podolsky, and Rosen, also known as EPR, and we will refer to it in the remainder of the talk as EPR. Schrödinger, Born, and Aronov and John Bell. There is also a physics path which is not known by most practitioners in the field. This path has the origin in a paper written by Dirac in 1930 and then projected further by Wheeler in 1946, which culminated in the work of Price and Ward in 1947. Now, why does this matter? Why is it good for us to know a little bit more about the physics side of things? Understanding the physics of quantum entanglement at a fundamental level can lead, I think, to better optics configurations and to improve a more efficient quantum entanglement technologies. So let's look about what we all know, or most of us know, the philosophical path. That path started with a paper by EPR in 1935. This is one of the most well-known papers in the Hall of Physics. The paper has two sections. The second section is predicated on the first section, and the first section concludes that because the spatial coordinate has an all-value resultant, therefore it is not a representation of physical reality, and therefore quantum mechanics does not provide a description of physical reality. That is to say, quantum mechanics is incomplete, and EPR expressed their hope in that paper that eventually there would be a more complete description of quantum mechanics. At the same time, in 1935, Schrödinger wrote two papers, one in 1935 and the other one in 1936. And this paper referred to, for the first time, to the word entanglement and also the word disentanglement in the context of the EPR description. Schrödinger was very unsettled by the fact that an experimenter in system 1 would have control of the measurements of an experimenter in system 2 when these two systems are separated by a long distance. He did not like that. Now, the Schrödinger paper was very much sent to the archives of physics for a long time, and it was nearly forgotten in the citation route. And it was not until the 1990s that the Schrödinger paper was again beginning to be quoted, and the words entanglement were brought back into the field. In 1957, Born and Aronov published another paper which was based on a book written by Born known as the Quantum Theory. And in this paper, Born and Aronov considered a thought experiment of two electrons moving in opposite directions with opposite spins. Born and Aronov introduced into the philosophical path some information from the physics path, which we'll describe next, particularly the results of an experiment by Madan Wu and Chaknov. And that paper did encompass most of the information, almost all the information relevant to the physics path. Another momentum paper was written in 1964 by John Bell. John Bell came up with his famed Bell theorem or Bell inequalities, and this paper restated that so-called hidden variable theories, that is, that possibility of an improvement in the description of quantum mechanics, these hidden variable theories were incompatible with quantum mechanics. Now, that was nothing new. Already 32 years previously, John von Neumann, in his book, The Mathematical Foundations of Quantum Mechanics, chapter 4, section 2, had expressed something to the effect the basis of quantum mechanics would have to be objectively false in order for hidden variable theories to be possible. So Bell just reinforced in a more lucid manner, if you can say that, the thoughts that were already known in the literature since 1932. That is to say, hidden variable theories are not compatible with quantum mechanics. Interestingly enough, there was a lot of interest in hidden variable theories, a series of papers, and even the aspect experiments were aimed at dealing with the issues of hidden variable theories. Now let us describe the physics path. This path was started almost in an unintended manner by Dirac in 1930 in a paper that he wrote on pair theory. Wheeler in 1946 came up with a scheme to test Dirac's theory. And in that paper in 1946, Wheeler came up with probably the best description of what quantum entanglement is, and probably the most lucid description of what quantum entanglement is. He was referring to the electron-positron annihilation, creating two gamma rays propagating in opposite directions. And he wrote, quote unquote, according to the pair theory, if one of these photons is linearly polarized in one plane, then the photon that goes off in the opposite direction with equal momentum is linearly polarized in the perpendicular plane. Wheeler, 1946. And that is probably one of the most beautiful descriptions of what quantum entanglement is. Now, in 1947, Price and Ward at the University of Oxford put down to paper the physics inspired on the Wheeler statement. And they came up with the probability amplitude for quantum entanglement as an intermediate step to provide a final equation for the polarization correlations of an X-ray experiment that necessitated quantum scattering. So it was a more complicated experiment than the usual experiments that we are familiar with now. A footnote here, and a very important footnote, is that the Price and Ward paper was published in 1947, and late in 1947, Richard Dalitz, an Australian physicist, recently arrived to Cambridge. Dalitz is known for the Dalitz plot, Dalitz pair, and the Dalitz pole, for those who are familiar with particle physics. Having knowledge of the Price and Ward paper, gave a seminar in Cambridge showing how he would derive the probability amplitude for quantum entanglement, which had been used by Price and Ward to obtain the results published in Nature. And those results were published in this half-a-page paper in Nature in 1947. The equation that you see there is the cross-section for the scattering. And on the left bottom part of that paper, you see the very first configuration description of what a quantum entanglement experiment is. So Price and Ward derived their probability amplitude for quantum entanglement, which using the Dirac's identities and normalization can be expressed as the equation in the second line, which is the equation that we all are familiar with. Now, the experimental drawing of quantum entanglement provided by Ward and Price is shown here in more clarity and detail. And if you make θ1 equal to θ2 and replace the scatterers by a polarization analyzer, then you end up with the familiar experimental setup that we use now in the visible spectrum. Now, in the 1947 paper by Price and Ward, an angle in the cross section is provided, which is delta 5 equal to 2 phi 1 minus 5 2. This angle comes again and again in the literature and is never referenced back to Price and Ward. In our book, Fundamental for Quantum Entanglement, that angle is called the Price and Ward angle. Plosa et al. In 1969 and others utilized local hidden variable theory arguments to dismiss the work of Hanna et al. And Blur et al. So let me go back here quickly to this slide. Snyder et al., American physicists, reproduced the same result of Price and Ward in 1948. Hanna and Blur and Bratt in 1948 produced the very first experimental results, and Wu and Sakhnov refined those results in 1950, and it was those results that Born and Aronov used in their philosophical path discussion. In 1965, as a footnote, in the Feynman lectures on physics, Feynman, considering Hamiltonians, came up with an equation which could be used as a basis to also derive the probability amplitude for quantum entanglement. In 75 and 76, Casday et al., Wu was a co-author of that paper, and Wilson et al. Provide refined results of that experiment now on full knowledge of Bell's inequalities. Plosa et al. In 1969 and others utilized local hidden variable theory arguments to dismiss the work of Hanna, Blur and Bratt, and Wu and Sakhnov, even though Born and Aronov considered the Wu and Sakhnov experiments legitimate representations of the EPR situation. Historically speaking, this skepticism eventually led to the experiments of Aspect et al., which are a visible optical version of the X-ray experiments performed by Hanna, Blur and Bratt, and Wu and Sakhnov. Interestingly enough, from a physics perspective, the Aspect experiments are amply justified simply from the perspective of repeating the X-ray experiments in the optical visible domain, where the physics is simplified significantly. A brief consideration of the Bell theorem. The main outcome of dealing with hidden variable theories was that work stimulated the creations of Bell's theorem, albeit in 1932, von Neumann had already proclaimed the incompatibility of hidden variable theories with quantum mechanics. Today, Bell's theorems is mainly applied as a tool to verify the security of quantum cryptography communications. let us consider a little bit now the EPR paradox, and paradox in inverted commas, because some physicists, and in particularly, I think it was Lamb, who sometimes said that paradoxes in physics are probably misunderstandings. The EPR paper, as I said previously, has two parts. The second part is predicated on the first part, and the first part depends exclusively on an all values spread of the coordinate, which implies an exact measurement of the momentum. An absolute exact measurement of P with delta P equal to 0 is physically impossible. Every experimentally knows that. And this is nothing new. Bohr tried to use the uncertainty principle to answer the EPR argument, but unfortunately, he wrote a 7-page paper that began to deal with issues of philosophy and did not convince everyone. Also, Dirac, in his book toward the end, clearly states that delta P equal to 0 or delta X equal to 0 is not possible. So with that in mind, we can rest assured that an all values spread of the coordinate is not possible. Therefore, we can conclude that quantum mechanics is not an incomplete theory. A most relevant statement in this regard: the two photons are entangled, and according to local realism, their polarization planes should become independent, a typical EPR situation. Already in 1948, observations agreed with quantum mechanics, not with local realism. Now, let's say a little bit about the interferometric origin of quantum entanglement. There we have the Dirac-Feynman interferometric principle that applies to a generalized interferometric situation, illumination by a single photon or an ensemble of indistinguishable photons. And if we apply that to a quantum entanglement configuration, we can show that from the Dirac-Feynman principle, we can arrive at the probability amplitude of quantum entanglement, provided we use one of the Dirac's identities. This is discussed in detail in chapter 17 of Fundamentals of Quantum Entanglement. Those equations can be generalized. These equations are shown there, apply to two channels and a pair of quanta. If you have n, which n is the number of quanta, equal to capital N, the number of propagation channels, equal to 2, 4, 8, 16, and so on, then you can derive generalized equations to describe situations such as the one shown here, with 8 propagation channels and 4 pair of quanta. There are now 4 definite ways to derive the probability amplitude for quantum entanglement. One is Ward's heuristic approach based on conservation arguments. Recently, I had a conversation with a well-known particle physicist, and he said to me, once he saw what Ward did, he said, this is precisely the way that a theoretical physicist would do it. There is also, a particle physicist would do it. There is also the interferometric approach disclosed in 2013 and in the book Quantum Optics for Engineers. The Hamiltonian approach introduced by Feynman, which can be extended to arrive at the probability amplitude of quantum entanglement. That's also shown in the book Quantum Optics for Engineers. And there is also a fourth way in which Pauli matrices can be used to arrive at the probability amplitude of quantum entanglement, which, by the way, are known in the literature as Bell states or EPR states. Now, let's look at some matrix identities using the vector direct product. If we write down the four possibilities for the probability amplitude of quantum entanglement relative to a pair of quanta and two propagation channels, and if each state is expressed in vector form, then we can show that each of those probability amplitudes or entanglement states can be expressed in a 2x2 matrix form. And that is very useful because we can express all the optical elements used on an optical table using 2x2 matrices in polarization. So if you look at closely, these matrices are the Pauli matrices. So there is a very, very fundamental connection in this physics, and there is a beautiful set of four identities that can be used to describe all the possibilities of the probability amplitude of quantum entanglement. Now, if we use a polarization rotator, 90-degree polarization rotator, such a half-wave plate or a double rhomboid or a multiple prism rotator, which can be represented as 0, 1, 1, 0 in a 2x2 matrix, then if that matrix operates on the different entanglement states, we again get a very nice symmetric set of probability amplitudes. Quantum entanglement and the Hadamard matrix. The Hadamard matrix is very well used in quantum computing, and if we make the Hadamard matrix operate on the different quantum entanglement states, again we get a very nice set of identities. And as you can, if you observe closely the equations, again there is a lot of beautiful symmetry associated with them. It's this set of results is important because if you look at the literature, some authors have tried to do this previously and obtain identities which are erroneous. So the results shown in this slide are not correct. These are the correct results, and you can find them in Fundamentals of Quantum Entanglement, chapter 24. Now, the experimental configuration of quantum entanglement lends itself very nicely to quantum communications. For instance, you can have space-to-space satellite communication arrangement, which fits the physics very nicely. Instead of two satellites, you could also have two receiving stations on the ground, as the experiment of Jean et al. In 2017 demonstrated. Now, toward the end of the presentation here, we are going to talk a little bit about the fundamental principles that are necessary. And these are all listed in this slide here. That is chapter 29 of Fundamentals of Quantum Entanglement. You have quantum, the quantum energy, the Planck energy, the uncertainty, the Heisenberg uncertainty principle, the Dirac-Feynman interferometric principle, the Dirac identity, and you also have Born's rule. In essence, that plus knowledge of algebra and vector algebra is all you need to handle the principles of quantum entanglement and do things from the ground up. There is a beautiful question that persists and that probably has not yet been settled. What is more fundamental? The Dirac-Feynman interferometric principle given in the first equation on the left, which can be used to arrive to the probability amplitude of quantum entanglement, or now that we know that we can derive the probability amplitude for our quantum entanglement from, let's say, the Pauli matrices, let us assume that we derive the Pauli matrices from first principles. Then we end up with the probability amplitude of quantum entanglement. Since this process is completely reversible, you can then go on and derive the Dirac-Feynman principle. What is more fundamental? Some people think the probability amplitude of quantum entanglement is. I tend to think more of the Dirac-Feynman principle, but that question, I think, has not been settled, and is a wonderful question to ponder. So, in summary, for this presentation on the fundamentals of quantum entanglement, all that is needed to solve problems in quantum entanglement are the Dirac-Feynman principles that adhere to the Copenhagen interpretation. EPR's arguments can be neutralized via Heisenberg uncertainty principle. Bell's theorem is a way to neatly dismiss the hidden variable possibility, which had already been dismissed early on by von Neumann. Hidden variables are incompatible with the principles of quantum mechanics. From the physics path perspective, the field of quantum entanglement rests uniquely on the probability amplitude of quantum entanglement. From a pragmatic perspective, the field is wide open for configurational improvements in the optics architectures of these free space communications, for instance. With the proper use of the principles outlined in fundamentals of quantum entanglement, there is no need to be concerned about interpretational issues. More information on the book is given in tunablelasers.com/fqe.htm. And if you have any questions, you can forward them to me at opticsjournal@gmail.com. And with that, I conclude this presentation. I hand this back to Evie.
Brilliant, thank you. Thank you ever so much, Dr. Duarte. We have had some questions come in, so I'm just going to try and get those up 1 second. Oh, okay. Just here. So the first question we have had come through, could you please comment on Bohm's role relative to the probability amplitude of quantum entanglement?
Yes, that is a question that we didn't quite focus on early on in the presentation. Bohm, in his book Quantum Theory, refers to a thought experiment of electrons with spins up and spins down. Toward the end of the treatment of that problem, introduces eigenfunctions, which are the probability amplitudes for quantum entanglement written in wave function notation. Those were the equations introduced by Snyder et al. In 1948, which were introduced without derivation, and Von does not provide derivation either. That type of writing the probability amplitude of quantum entanglement used anymore. Everyone use the Price and Ward way, which includes uses the Dirac bracket notation.
Okay, thank you. Another question, you did refer to the generalized cases for Bell's states 4, n equals 2, 4, 6, 8, 16, etc. What about n equals 3, 6, 9, and so on?
Yes, that case, the case for n lowercase n, large case n equal to 3, 6, 9, is treated in detail in chapter 19 of the book, and it involves some very nice mathematicals known as Hamilton's quaternions. So for details, refer to chapter 19. Chapter
19, okay, brilliant, thank you. Can you comment on the relative contribution by Price and Ward in the development of the probability amplitude for quantum entanglement, and also clarify once more the Dallet's contribution?
Yes, it is not well known how these things came about, like whose original idea was it Price or was it Ward, or was it an interaction between the two of them? With the many conversations that I had with John Ward, I never asked that, and he never mentioned it. All I know is that when Ward wrote the paper for Nature in 1947, Price did not want his name to be included, but Ward insisted. So that is still a little bit of a mystery. In regard to Dallet's, Dallet's provided in his seminar in Cambridge in 1947 his own derivation. What derivation was that? We don't know unless someone took notes of his seminar. That is another little mystery, and I personally would like to know what was that.
Oh, so it will just still remain a bit more of a mystery then?
Yes.
We've had a couple more questions. Somebody's asked how many qubits are possible in quantum entanglement experiment?
Well, that's a big question, and I don't think I know the answer. You know, we would like eventually to have thousands, but now you know that there's been very slow progress in that area.
Okay. Going back to Bell's theorem, somebody's asked if you could expand a little bit more on that. You don't seem to emphasize Bell's theorem. Could you expand?
Yes. Bell's theorem, let me go back. Bell's theorem is what I said, it's mainly now used as a tool to determine whether the quantum cryptography communications have been compromised or not. In Bell theorems, you have the sum of 4 probabilities which are evaluated from the probability amplitude of quantum entanglement. And if there are hidden variable theories, then that sum should be equal to less than 2, but the experimental data always give results greater than 2 and nearly like something like 2.8. But the most use that I see nowadays of Bell's theorem is as a tool to determine if the communications have been compromised or not.
Thank you. We've just got a couple more questions. So,
Yes.
Can a photon be entangled with itself in its different degrees of freedom?
Yes, I think, and that is discussed in one of the chapters in the book. Let's see, if you have, for instance, an N-slit experiment and with single photon illumination, then the probability amplitudes through each of those slits are severely entangled. So the photon is entangled via the entanglement of the probability amplitudes, and severe in the case of interferometry through an N-slit experiment. That is discussed in chapter 20 of the book.
Brilliant. Thank you. I think we've just got time for one more question.
Sure.
So the first one we're going to ask is, could you comment further on the fundamental importance of interference relative to quantum entanglement?
Yes, that is it's a very important question, and let me say this. Remember what John Ward said. John Ward said xy minus yx was the most important thing I learned in quantum mechanics, and the rest is just mere technique. So if you read the statement, he seems to attach great importance to that learning, and there are many who do think that that is the most fundamental statement of quantum mechanics. However, the same John Ward in his writings said, quote unquote, something along the lines, we tried to do these calculations, but he neglected to include the interference terms and therefore derive an erroneous result. This is a great question, and a question that needs further clarification.
Thank you. I think what we'll do is, there's just a couple of other questions that have come through, so we'll try and get you to answer those separately, and we'll find a way of getting those out to people. But unfortunately, that is all we've got time for today. So thank you ever so much, Dr. Duarte, for your presentation, and thank you everybody who is listening, taking part, who have put a question to us. Really appreciate it, and we hope you found it of interest. There should be a rating button on the presentation screen, so if you're able to rate this, that would be really helpful for us as well. And please tell your colleagues about the webinar. It will be available to listen on demand within the next 24 hours. Also, the book Fundamentals of Quantum Entanglement is available to download from our website, iopscience.org/books for purchased institutions, and for individual purchase via Amazon and other online retailers. So please check with your librarian for access, and if you don't have access, recommend it to your librarian. But thank you ever so much for joining us, and the webinar is now over.
Okay, thank you, Evie.
Dr. Duarte.
Thank you.